In progress. Audible?
It's audio.
Hello. This is the equivalent circuit as referred to secondary side. So actually here we made some this circuit with respect to as referred to primary side. Then this vector diagram will be see this is V2 because here is your cos phi 2. Okay, so this is your V2 days. Correct, V2 days. Then this is your current if it is lagging or leading. Suppose lagging power factor I2 days. Okay. This is your phi 2. Or generally here we take this because as a I1 this current. Okay. Correct, because we consider this I1 equals to I2 days. Because I0 we have to neglect. Okay. So this is I1. Okay. Then drop due to here as referred to primary side. I1 because it is I1 now, total resistance R1, and this is your reactance drop I1 X01 total. Then this will be your V1. Okay, V1. V1 means E2 days. We can write this is E2 days. Okay. Therefore, in your when we write this regulation, voltage regulation percentage, it should be as referred to primary side, which is greater here V1 minus V2 dash by with respect to V1 we calculate as no load. Correct, into 100. So this is your voltage regulation. Okay. Okay, here is also with respect to E2 no load voltage we have to calculate. Okay, either no load or this. Okay. Correct. So this is the as referred to primary side. This is the formula as referred. This is as referred to secondary side. Now here, when we calculate V1 minus V2 dash, it is I1 R01 cos phi 1, primary side cos phi 1, or either you take as a phi 2, okay? Or phi 2 load plus I1 x0 1 sin phi 2. Or let us we write here I1 phi 2 overall transfer, so this overall power factor, then divide by V1. Okay, dear? Actually, here one question is there. We introduce now. This is very important. This one. This first B. Okay, here we take this. As I told, the result obtained from a 50 kVA transformer open circuit test. So first open circuit means load test. So yes, it is one as per your transformer question, latest. It is recently asked in your exam paper 1B. What is the your short circuit open circuit test? Here we write short circuit test. So in open circuit test we apply the rated voltage. Correct? That is V1 3300 volt. Then we are here in secondary also we measure the voltage V2. That is also we get a 415. Actually these are primary here. These are equals to your induced voltage also, because it is no load voltage, correct? At no load, it is no load. At no load. Then you write. Now when we apply at no load, there is a power input. So this no load input power W naught is, it will give the iron losses equals to core loss. Please remember, equals to, that is generally your B1 I naught cos phi naught, means no load input power. This equals to iron or core loss. Okay, no load input power. So from open circuit test, we measure the no load or core loss as a, it is core loss means iron loss. How much it gives? It is power is given 430 watt, or you can write 443 kilowatt. Okay. Now on short circuit test. In short circuit test, here we apply the reduced voltage because in open terminal voltage, this is your transformer suppose, and this secondary is kept open. Therefore, here V2 and here E2. This E2 equals to V2 equals to 415. But here in primary, we give the V1 rated voltage, that is 3300 volt. And there is a I node, no load power input, okay? But because it is connected to your supply, voltage, okay? In short circuit, on HV side, here we apply the reduced voltage. Here we apply reduced voltage like VSC. So this is your secondary side. Now it is shorted. The secondary is shorted. Here we also measure the current ampere. So it is ISC, short circuit current is measured, and here this is the applied voltage. Okay, so here it is your what is the input current. Here we can measure that. This will give you short circuit current of transformer. Okay, secondary one I measure. Okay, dear. So here the short circuit current is flow because it is short circuited. Then when your transformer, this emitter take a rated ampere, then we note down the rating. We increase the voltage till your transformer will take a full load current like. So here this VSC is applied voltage, short circuit, under short circuit, what is the voltage? This on short circuit test, primary voltage, this VSC, it is 120 volt. Primary voltage. Primary current, here we measure this ISC. It will give you 15.3 ampere.
So short circuit voltage is 124.
Sorry, 124. Short circuit power factor. This is also given. Short circuit power only given. Power on primary side. So what is the power input during this short circuit? 25. You know, this is equals to the power input by transformer is considered as a this is copper losses, total copper loss. Okay, so it is here copper loss. Correct? Means that is denoted by copper loss. Okay. So this copper losses in kilowatt, it is 525 watt. Now what is that? Second, can assume to the at a full load value. My dear, he said that secondary current to be measured. During short circuit, here we also measure the current when it is this take a like it is full load current. I2, full load current. Full load current. when your secondary carry the full load current, then we note down this parameter. Okay, so it means this will give you full load copper loss. It is full load copper loss. Okay, this is. Now please, from this data of short circuit, we also calculate because these are primary side, then we can calculate it is total equivalent impedance as referred to primary side. That is the ratio of voltage to current. Apply voltage to current. It is 124 by 15.3. This value will come 124 divided by 15.3. It comes 8.1046 ohm. Then we calculate X01. Before this, we calculate the copper losses also. Copper loss are given full load copper loss. So what is the total full load copper loss as referred to primary side? Then primary current into total resistance as referred to primary side. Okay. So this is your I1 is now this is the primary current, 15.3 square. This equals to your full load copper loss. Okay. This will give you total copper loss. Okay. This value is there. 525, sorry. Watt. Then we can calculate R01 equals to 525 divided by 15.3 square. 525 divided by 15.3 whole square. It comes 2.2, 2.243 ohm. So this is the resistance. Okay. So this is your. Now we can calculate X01. It is impedance square minus resistance square and root of this. So this we can write 8.1046 all square minus 2.243 all square root of this square minus 8.1046 square 60 divided and root answer 7.788 ohm. Okay, all parameters we get. Now we come to the question part. What they ask? Efficiency at full load and half load. See, first part, efficiency at full load and efficiency at half load. Okay, so For this, first you calculate what is the kilowatt output of transformer. Kilowatt output at full load. Here you write kilowatt output at half load. So this kilowatt output at it is a kVA rating. kVA into power factor. Correct, no? 50 kVA, the power factor he said that at 7 lagging power factor, 0.7 power factor, load power factor. Okay. And here, what is the at half load? Your half rating means 50, sorry. If you divide 50 by 2, so 25 it comes. Half capacity, okay, half load into power factor, again same. Now see, 50 into 0.7, 35 kilowatt. Is 35 kilowatt power output. Here it is. $17.5 kilowatt. Now half load, this is full load. Now total losses at full load. So your iron losses are called constant load. This iron loss plus full load copper loss. Okay. So it is iron losses are this, copper losses are this. Open circuit power is equals to core loss, short circuit power equals to copper loss. Please remember. So this is 430 plus 525. Four 30 plus 525. 99. It comes 955 watt, or it is 0.955 kilowatt. Okay. Same here. What is the total losses at half load? Total losses at half load. So at half load, your copper loss will change. That is at half load, they become 1/4 square time. So your iron loss are fixed. That is 430. Iron loss plus copper losses at half load. Okay. So it is 1/4 of full load copper loss. Why it is? Hello? Because the copper loss are variable loss. Suppose that, when, suppose this is your load, if it's connected to supply, if we talk about the load current, what is the load current? Suppose kilowatt load. So this kilowatt load into 1000 to convert into what? Divide by here √3 into voltage. And there is a power factor. Okay. This is the load current. Correct, no? √3 VL cos phi. It means if your load is half, if this kilowatt load is half, then your load current is become half. If load current become half, then the copper losses due to this current. copper losses are square time of load current, square time into total resistance. So if your current, if load is half means current is half, then square time losses, they become 1/4. Please remember, if load is half, your copper loss become square time means fourth. If fourth time means 1/4 only load, then 1/16 time your copper losses. If load is double, then it is increased. Okay, so your copper loss are depends on load, but iron losses are not depends. Either it is zero power factor, zero open circuit, or it is half load, full load, they are same. It is clear why this copper loss are half at 1/4 of full load copper loss. So my dear, it is 4.
सर एक बार और बता दो.
Yeah. Your full load copper loss is 525 divided by half 4. See, if
सर एक बार और बता दो.
yes. Suppose here we talk about when at no load. At no load, why we neglect the copper loss? Because no power output. Generally, it is very less current is take. Correct, no? So this total power input is take as a core losses because it is utilized in magnetization only. But when we put a load here, the transformer take a load current here I1. Huh? Now it is I2 here load current. I2 dash. So see, if there is a full load, then full load current. But if you half load, your load is half, means this current are half load current. But your copper loss, na, if we calculate a copper loss, that is square time of your total load, equivalent load, resistance, sorry. Yeah? This is your losses, na, and this is your load current, or either secondary side you take I2 square R02 as referred to secondary side. So here is the direct relation. See, suppose here is a 100 kilowatt load. Then we can calculate the current I2. If we double the load, like 200 kilowatt, then current will double. Then current will double, then power losses are square time of that current. Square time means if you double, then your copper loss also become 4th time. If we reduce means from, if there is a full load copper loss is 200 kilowatt, now we reduce to 100 kilowatt. So total less current. Suppose it is half means if load is half, current is half, but copper losses are square time, no? When we calculate a copper loss, square time of current. So as compared to earlier math, earlier, now if load is half, then your current is half, means copper loss become 1/4. Okay, current half means half load means current is half load current. Then current is half, then copper loss, you know, that is square time of current. Means copper loss are depends on load. What is the load on the transformer? So this is become 1/4. Current is half means, and your copper loss are square time I square R. So it comes 430 plus 13 1.2. 131 watt, or it is 561.25 watt. This is the kilowatt loss as a total. So this is the difference, at full load, and this is at half load. Now, efficiency. Output of transformer by input, and output divided by output plus losses, total loss. Input means output plus total losses. In total losses, your total losses are iron plus copper loss, same here at half load. Output by input the output is now this input means output again plus losses. So now here is also total losses. Just you put the values. Now what is the kilowatt hour? Here it is 35. Here it is 35 plus total losses are 0.955 here. Here it is so here is the output is at half load, it is half, no? 25 kilowatt.
Sir, 75, 17.5.
Yeah. यहाँ पर फिर ये okay 0.7. This is 17.5 kilowatt divided by 17.5 in plus total losses are here 0.561. Okay, into 100.
$97.34 and 96.85.
This is 90.
7.34.
7.34%. And this is
96.85. 89.
so like almost means same as 20. It is that's why now this see here your efficiency low, because we are operating the transformer at half load. That's we can say na, we optimum sizing we do. If your equipment run at partial load, their performance is down, means efficiency and load. Because for same iron loss, your kilowatt output is less. Okay. Now is this question has another part too. Now we say that voltage regulation at 0.7 lagging and leading. Now you take you consider 0.7 lagging power factor and leading power factor. Okay. Like here. And terminal voltage also in third part. So see, they ask voltage regulation. Percentage voltage regulation at 0.7 lagging power factor. Here percentage voltage regulation at 0.7 leading power factor. My dear, here power factor we consider it as because we have a parameter as referred to primary side. Your parameter are this, we have calculated this R01, X01. So this X01 is 7.7788 and this is 2.24. Please, R01, X01 and cos phi 1. Let us be consider in which no load for transformer power factor has input. So this is 2.24. $2.243. 2.243 on X is 7.788 on your power factor cos 5. It is 0. Power factor is given 0.7 and 788. So 0.7 is given lagging. Suppose here first we consider a lagging power factor. So now we calculate 51.7. So the cos inverse of then sin phi 1. Seven one four, huh? My dear, as referred to primary side as right, percentage voltage regulation. It is V2, sorry, V1. It give you V1 minus V2 dash by V1 into 100. Or if you are a formula, if this we calculate, na, V1 minus V2 dash, that is I1 R01, I1 R01 cos phi 1 plus I1 X01 cos phi 1. Sorry, sine here. This is sine, okay? Correct, as referred to primary side. Divide by V1, okay? So just you put the value. I1 means, you know, it is 15.3 current at primary side. It is because secondary side when full load, this is your primary side current, okay? Into resistance is 2.243 into 0.7 plus 15.3 into X0 7. Two four three. This is 7 and 15 into 7.788 into cos phi is 0.714. This is your divide by, you know, V1 is, okay, please do not put here 415. It is V1, that is 3300. For percentage, you have to multiply with 100. 0.714. It is your sin phi into 7.788 X2 into 15.3 plus 15.3 into 2.243 into 0.7. Total comes 109.117 into, so divide by 3300 into 100 if we do, percentage voltage regulation will be your
3.30.
very good into 100. It comes, yeah, 3.36%. Okay, dear. Sorry, now we calculate this at lagging, leading power factor. Leading. Again here same, cos phi will be 0.7. Then we calculate phi 1. Cos inverse okay. Same is 45.57. But at leading power factor, this angle is negative, minus. Okay, this angle will come negative. (45.57). Then if we calculate sin phi 1, it will give negative value. What is the sin phi value? It's point. Due to this negative, your formula V1 minus V2 dash voltage regulation as referred to primary side. So this comes again I1 R01 cos phi 1. Here it is negative. Please remember. I1 X01 X01 sin phi 1. So due to this negative value, it is comes negative, or simply you write for leading power factor, it is negative. Divide by V1. Now here I1 again 15.3 into R01 2.243 into 0.7 minus 15.3 into 2.243
7.78 X01.
yeah 7 sorry there is a distance now. 8 times is 7.788 into power factor is sin phi value will be same 0.714, but it is negative. That's why here it is negative. Divide by okay. Here if you do 15.3 into 2.243 into 0.7 minus 15 into 7 7.15 just a minute 15.3 into 7.788 into 714. Here it comes negative 61 because so please there is a one question at leading yes this voltage regulation it depends on power factor. At lagging power factor it is positive, at unity power factor it is again positive, but yes, at leading power factor it is negative because your output terminal voltage is higher than your induced voltage due to capacitive load. Again with respect to V0 and V1 divide by 3 0. Okay.
Sir, sin phi 1 we should take plus or minus.
Sine
Sin phi 1, sir, plus 0.714 or minus 0.714.
it is negative, no? Sine phi is 0.714 minus 0.714. That's why this negative sign is come no, here.
Okay.
And now it become percentage drop now. When we calculate as a percentage, so it is 1.85% negative. Okay, so this is the voltage regulation in both cases. Now in third part, he is asking the terminal voltage. As I told, you please draw the secondary circuit, you know. Suppose this is total resistance, total reactance. Here it is E2, induced voltage. Then here, this is your load. This load terminal voltage is V2. Is induced voltage. Now due to drop here in secondary, you know, R0 to X0 to. Okay, this voltage is V2. Now there is a current due to this load current. When load current is flow, there is a drop in here. Then what is the here change in V2? He said that suppose this is given, you know, let us it is 415 induced voltage. Okay. Now he is asking V2. What is the terminal voltage? Third part. Terminal voltage output secondary voltage. V2 equals to, you know, there is a drop na here. Now this is in percentage is given. Then this. It means if you write na E2 equation, E2 equals to V2 plus or minus. Actually, if it is greater, na E2 is greater, then it is plus percentage drop. Okay, into point, how much? 0.33306. No? This percentage. If percentage divided by this, na, it is per unit. Na? 0.3.308. Okay. So this percentage drop, we have to subtract. Now he is asking V2. This V2 here, then this is E2 minus into, now we put the values, or E2 into percentage drop. Drop actually of this percentage drop of how much it is? Now this is 415 minus 415. This steps and do not write off. Maybe you can do. Okay. So it is 0.03306. Four 15 minus 415 into 0.033. This comes 401. Here also secondary load terminal voltage V2 equals to E2 VD voltage drop in per internal. VD is same 415 and this voltage drop is 415 of what percentage? Negative, man. This is again negative minus point, sorry, a 0.0185 you can write na percent. My dear, negatives become positive. This 415, sorry, 415 negative will become plus 415 into 0.0185. Okay, so it is plus. 185 plus 415. My dear, this comes this value will come 422 point. We write here. This is 7.677. Okay, so see, this is higher than your no load voltage. Why? Because at leading power factor, your your voltage regulation is negative. And you know, in long transmission line, EHT long transmission line, there is a one effect you have read, current effect, you know, corona effect, then scene effect, proximity effect, then current effect. These are the related to transmission line. Okay, power engineers, have you heard about the current effect? What is the current effect? Okay, current effect is in the long transmission line. You know, there is this is resistance of line, reactance of line. Maybe due to the capacitance, this shunt capacitance. Here, you know, this is the sending end voltage. Here also we read the line, you know, line regulation, voltage regulation. So due to this high shunt reactance, Your receiving end voltage is greater than. So your receiving end voltage is greater than the. So due to this, na, sometime this VR is greater than sending end voltage. That is called Ferrand effect. Due to the shunt capacitance, because long transmission line to ground is a capacitance is very high. Okay. So same like in transformer or alternator, if your load is be connected capacitive load. Okay. We require capacitor load when to improve the power factor. When you are in circuit, you are lagging AVR is more. But if load is power factor, then also this is not a good. Okay. Please, this question is okay now. First of all, your parameters, then efficiency at half load, full load, then you have to calculate the parameter. Then voltage regulation and terminal voltage. Okay. Just you subtract that voltage drop. So this voltage regulation is nothing but it is the drop, percentage drop. Okay. Now any other question you want to discuss in transformer? Yes, please. Otherwise we move in the next chapter. So next chapter. Okay. Any question? Doubt in transformer, please. As discussed, transformer efficiency. Because output by input, then output by output plus losses, total losses. Now this total losses are type of, this was a question asked in power transformer, which type of losses are there? You have to explain different type of loss. So there is a copper loss, I square R loss due to primary and secondary winding resistance, and there is a core loss that consists of hysteresis and eddy current loss. Okay. So this is the losses. Please to note down, this question was asked earlier in ETO, different type of losses in transformer. Hysteresis, eddy current, this is iron loss or core loss. Copper loss are due to. Here, na, this is actually, equal sign. is equal signature, equal. As referred to primary, this is as referred to secondary. Now condition for maximum efficiency, like they ask na condition in maximum torque, what is the condition? Sorry, in transformer I think it is asked na condition for maximum efficiency also. Yeah, no? This is the maintenance.
Sir, what about the C, 2C, sir? Protected device.
Yes. Protective device that are fitted on this large electrical transformer. So, you know, for oil type, if it is a not a dry type, oil type, there is a because relay also as a protective device. Silica gel breather also. But in dry type, we put a thermocouple immediate. There is a we measure the temperature continuously, monitor the temperature. In dry type, there is no transformer cooling oil is there. Your insulation is cast resin. So if due to overload and maybe there is this temperature is increased. If temperature of winding is increased, then insulation may be damaged. So we provide the like your temperature monitoring sensors. We put in thermocouple on the winding and insulation surface so that we can measure the continuously. Other protective are like open circuit, short circuit. In large transformer there is a differential protection relay also there. So you write the protective devices, protection. So there is a tap changer also. Okay.
What sensor, sir? Tap sensor.
Tap changer for voltage fluctuation to control the voltage fluctuation. So, in large transformer we provide this lighting arrestor also at HT bushing, HT side, correct? Okay, if your HT is like 33 kV or 6.6 kV, so there is a lighting arrestor also on HV side, okay, because it is high voltage. Right? Then CTPT protective devices they require, okay. Now
D, sir, maintenance requirements in there.
maintenance also, periodically schedule maintenance, preventive maintenance. Like in all type method, we also monitor the oil condition, but here in dry type, actually dust deposit we have to remove. On windings, if dust is deposited, then it absorbs the moisture. Then there is a causes of your maybe your insulation leakage current will this. So means there is a cleaning, okay, removing of dust on in dry type. Terminal tightness and the protective device we do the That is maintenance. Na? In oil type, there is a large maintenance, but dry type, there is less maintenance. But removing of dust, we check the devices. Okay.
Sir, doubt, sir. We cleaning, we are using vacuum cleaner or normal any brush or what?
Brush killing the dust, remove the dust, or you do the vacuum cleaner also. But you have to shut down the transformer, no? You disconnect.
Open the transformer and open the all panel covers after we clean that. Use vacuum cleaner and check the insulation and the tightness of the cables only.
I will bring tomorrow. There is a, one, like any manufacturer, there is a Kirloskar and some Impex transformer. They are manufacturers. They give the manual, operating or maintenance manuals. So that point you can, I will put a. This condition of maximum torque was asked in induction motor, not in transformer, है ना? But here is also the condition for maximum efficiency. Okay. So suppose what is the general equation for efficiency of transformer? Your transformer output by input, huh? Or this output we can write secondary side, na? Secondary side voltage, secondary side current, then secondary side power factor output. Okay. Now divide by, this is your output, power. Same like your input, we can write output plus total losses. So this output is V2 I2 cos phi 2 output divided by output here also V2 I2 cos phi 2 plus total loss means iron loss plus full load copper loss. This will give you efficiency. Okay. Now for maximum efficiency. So if you differentiate this efficiency eta with respect to, because we see this equation, it is your efficiency depends on load current I2. Other parameter we maintain constant. So if we differentiate this efficiency with respect to I2, load current, okay? This. Okay, if we differentiate I2. Okay, and set equals to 0. So again, if we d by d I2 of this entire equation, V2 by I2 cos phi 2, V2 I2 cos phi 2 plus W naught plus copper loss and set equals to 0. So by UV by V method, you have to differentiate and set equals to 0. Then we get a condition, iron losses constant equals to copper loss. Full load equals to your copper losses and load. Okay, equals to copper loss. Your iron loss equals to copper losses. This is the condition for okay. Now, actually, power transformer. power, if we talk about the power transformer, they always having a full load capacity because they are power, like, sorry, not power means which is used at generating station and in transmission line. But you know, distribution transformer, if we talk about the distribution transformer, like this. So here, you know, there is a load. It depends, this load is vary. This always, this transformer not at full load because it depends on the daytime, night time, morning, early morning, then season also, winter, summer. So load is vary. That's why these transformers are not designed for full load. Actually, generally like motor, electrical motor, the load here. It is when it connect, then this design when there is a full load. When there is a full load, this motor efficiency is high, means performance is better. So they design for full load, even alternator also. When there is a full load, the efficiency is high. Okay, at full load. Power transformer which are used at generating and transmission line, that is also designed for full load condition. But this distribution transformer, there is a there is a less time. Out of this 24 hours, the load is very like this on transformer. So see, only in narrow time period that has a, because this is MD, so your transformer designed for maximum demand. This has a like 100 kVA transformer. So this 100 kVA load is not all the time. There may be a 50, 70, then it is 90 degrees. Maximum time is your base load only, not a peak load. Okay. Therefore, now as you know now, at half load, the efficiency is low, means at partial load. Okay. The actual load on maybe it is 80 kVA maximum, average load. That's why your distribution transformer designed for a partial load. Means they give the maximum efficiency. So what is the kVA load? Corresponding to maximum efficiency. Okay, that we can calculate. Rated kVA into, if you know the iron loss, divided by full load, copper load. Audible? So if you know, yeah, please, audible?
Yes, sir.
Yeah, so if you know the full load copper loss and iron losses of a transformer, then we can calculate what is the load at which this transformer give the best performance. Means KVA load. This is KVA load, please. That we can put so that it will give the maximum, because this distribution transformer designed for partial load, not at 100% load, because maximum time is there is a part load on, not a full load. Okay. Here, this is your, see, like here, he does by primary side, but we have considered secondary side also. Okay. This condition you remember, copper loss equals to iron loss. Then see, as I told now, load at which two losses are equal. Two losses are equal means maximum efficiency. That is full load. Full load means rated KVA. Iron loss by full load copper loss root. Correct. Now that's why now all day efficiency we define for a distribution transformer. Now come to the three-phase transformers. Okay. So we either a single unit, three-phase unit, that is called three-phase unit transformer. There is a three-phase core we use. What is this? Actually, overall, it is a size is compact, but it is a single unit. Now, large as compared to now, I will tell you. See. Now we come to hello. Now this is a second part of this chapter, three-phase transformer. Okay. Three-phase transformer we take. Again the transformers. So construction, only the core construction is three-phase, is designed for three-phase. But working principle are same. There is but here in three phase, three primary, three secondary, correct? In single phase only two windings, one primary, one secondary. So how we construct a three phase transformer? Either there is a one type is a bank of three identical bank of three identical single phase transformers. So this is a bank of three identical single phase transformer. Three single phase transformer. Okay. Identical, you can break it. They are same. Or we have a three phase unit transformer. So there is an advantage and disadvantage. Here, when talk about the bank of three phase transformer, there is there is a three units, different single phase, but identical, same, like same turn ratio, same their percentage impedance, okay, voltage ratio. Okay, these are three identical बने नहीं है ये वैसे. Okay, so here, you know, 3 primaries, 1, 2, 3. 3 secondaries, okay. So here, if you, now we can connect this 3 primaries either in star or in delta. Okay, we can make like if we connect in delta, then you this 3 this you have to short, and we give the supply here, here, and here, or like here also. This you have to short, and you give the supply to this. So it is called star star. Maybe delta delta star star. Okay, like this. Okay. What is the advantage here? See, this individual unit, first we take the advantage here, bank advantage. Individual units, they are easily we can lift and shifting. Okay, movement easily. We can transportation is easy, light in weight, no? Okay, then suppose spare part of transformer 1, this is TR1, suppose, TR2, TR3, or spare part, same spare part we can use in anyone. Pardon? Suppose here but here disadvantage is we have to install independently this 1, 2, 3. And co-star is more. This is disadvantage because if we brought a 3 units, you order 3 units, cost is, initial cost is high, and large space is required for installation. We have to monitor the R3, means all 3 units. So their maintenance, but spare cost is reduced. They can, easily transportation easy. Next is the another advantage. Suppose it is only not a chance ki all 3 are fail at a time. Suppose one transformer is fail or become a damage. So only this we have to remove, replace. So your cost of replacement is low. Otherwise, in this unit bank of transformers, we have a 3-phase core. This is what we do now. Like R phase winding, LV, Y phase, then B phase, LV. Now over this LV, we put a HV winding. So these are the all HV, LV here, R phase, Y phase, B phase. Okay, here also 6 winding, but they are this is the unit bank of three-phase transfer. Okay. So see, only we brought one single unit, large unit, but now only one unit I have to install. The initial cost is less, but suppose this core is damaged, then we replace the entire unit, but it is large cost. Okay, cost of replacement. So there was already I shared this notes, I think, comparison. I put already in group, compare the advantage of bank of transfer. Yeah, here it is. In earlier it was in ETO, it is asked, and see, bank of three phase and single unit three phase transfer. It is a bank of three single phase transformer and it is single unit transformer. Okay. More costly due to more iron, three separate tanks, more oil, more auxiliary component. Initial cost is high. As a three separate transformer, it required 6 HT bushings. More floor area is required for installation. Capital cost increase. But here the advantage is another now advantage. One another things we have forget also here. See, suppose on board your transformers are mostly delta connected. Why? So suppose delta means this all three primaries we have connecting delta. Then on secondary side, load side, it is also connected in delta connected. Okay, so in delta, if suppose this is transformer B, means B phase. This is used for R phase, this is used for Y, this is B. So any one, suppose Y phase is gone, this third transformer or second. So like this is this winding, this we have to remove. Correct, na? So if suppose one transformer is damaged, then we can connect, remove this faulty transformer, or temporary means for some period when your second unit will come, new unit, and we replace it. Till that we can use in open delta. We operate in open delta. That is called VV connection or open delta, or it is called open delta. Open delta connection. In that, we can operate R, Y, B. We get a three-phase supply also. Okay. Okay. But your capacity, reduced capacity, your capacity is reduced by 1/√3 times of rated capacity. Okay. Like if it is 100 kVA transformer, then we can only 57 kVA it will operate. 1/√3 times. 100/√3 means 57.74. kVA we can operate. Okay. open delta we can use. So here it is written, if one transformer damaged, then it can be easily replaced with a single unit only. But here, one phase is damaged, then whole transformer it will be replaced. Here. Now suppose only one single phase transformer required a standby unit. But here complete transformer we have to need a standby unit. Because of more iron, it is less efficient comparatively. This is highly efficient because single unit and losses are less. Overall, there is a loss in 3 units, no? 3, okay. Easy transportation, but here it is large, it is difficult, okay. Got it? Now this is your, now if we talk about the 3-phase transformer, this is a 3-phase single unit, okay. Now if we talk about the connection, it is either star star or delta delta, star delta or delta star. Then V connection. V means open delta. This is Scott connection you have to forget. It is a like a special connection which is used for to give the sub to feed the furnace, means electric furnace, heating for. Only this star star delta delta star delta delta star and open delta or V connection. Sometimes zigzag also ask. Zigzag is also a star part. So this is the connection. If there is a 3 primary, 3 secondary, now we can connect in star star or delta star. Star delta or star star, or it is interconnected means it is a zigzag, star zigzag, okay. So this is the connection, 3-phase, star connection, delta connection, okay. Now, before you study the 3-phase transformer, we should understand the 3-phase terminology. So, you know, in 3-phase, there is a line voltage. Already we discussed it is in 3-phase. There was a question, na? Star delta connection. So this line voltage means voltage between lines. Phase voltage means voltage between line and neutral. Now if we talk about the balance star, here line voltage equals to √3 time of phase voltage, and line current equals to phase line current equals to phase current. Delta voltage, line voltage equals to phase voltage, but phase voltage means voltage across each phase coil, and line is between the lines. Current, line current which is flow in the line, and phase current in the winding, each winding, okay. So this is the construction, like why we required a 3-phase transformer, because our major generation and distribution are in 3-phase. That's why we required a 3-phase transformer. Construction, like a 3 single phase transformer bank or using a common core of 3-phase winding. ये 2 ट्रांसफार्मर वाला छोड़ दीजिए. This is for stop Scott connection है. D नहीं, A and C it is only है. This is the connection for 3-phase transformer, star star delta delta or star delta star delta star, or maybe V open delta है. Correct. Now please remember, when we study the 3-phase transformer, we use the turn ratio per phase or phase transformation ratio, phase turn ratio, per phase turn ratio. It means secondary phase voltage by primary phase voltage, and this N2 by N1 phase winding turns है. It only one coil है. There are 3 primary, so we have a per phase number of turns है. That's why it is a phase turn ratio. Please remember, when we calculate a turn ratio of 3-phase transformer, we take a per phase value. Okay. Now star star connection. So there is a advantage and disadvantage. There is a merits and demerits of each type of connection. Star star, it is this connection is satisfactory or it is suitable for balance load. Balance means RYD. All 3 windings have a balance load. Like in motor, windings are balanced, each number of turns transformer. But we do the load on this, like a alternator are connected in star star. But if there is a load distribution on RYB is different, then there is a neutral leakage current will be there. Huh? Okay, that's why. But you know, because this, what is the voltage across each winding in this star connection? Phase voltage means 1 by root 3 times. Per phase, less number of winding or voltage is also 1 by root 3 times. That's why less dielectric insulation material also reduce. Okay, there was a sometime question is asked, why your alternator is always star connected? Alternator means generator winding. Yes, please, AC generator. Hello? There is an advantage in star connection. Why? First off, why each voltage across each coil is less, 1 by root 3 times. Delta connection, it is line voltage equals to phase voltage is also equals to line voltage, correct? But here voltage is less means your like in 11 kV alternator. So your voltage is reduced 1 by root 3 means your saving of insulation material, less insulation is required. Second, star point we get for neutral grounding. Then earth fault protection we can easily provide. Okay, that's why your alternator and we have to. Now come to the delta connection. They are used for moderate voltage. Now there is an advantage also delta. First is stable for unbalanced load. That's why on board transformer are generally delta connected, correct? Why? Because here we not require have a neutral. And see, this is suitable for unbalanced load. And what is the advantage now? Delta. If suppose one transformer means one phase is fell, one winding, yeah? One transformer fell, then we can operate in open delta, we can run. So your total blank out will not be there, correct? Then here in delta, this third harmonic component is eliminated naturally. But in star, there is a disadvantage. Hello? It is not suitable for unbalanced load. If there is unbalanced load means neutral leakage current is there. Third harmonic will be present in the transformer secondary. And there is a third harmonic current is there, so that losses are high. But this third harmonic is eliminated in delta connection. Okay, so it is star delta, delta star now. Okay. Now, when the transformer are connected in star delta or delta star, there is a 30-degree phase shift between the primary and secondary line voltages. So hence, see, when we select we go for a parallel operation of 2 or 3 transformers, so we should only select the same configuration, like either all are star connected, all are delta delta, or star delta either. Like we cannot operate suppose one transformer is star and we cannot parallel with star delta. Okay, why? There is another term in three-phase transformer, a paralleling condition, desirable and essential conditions, parallel operation. First of all, one question is asked, why this line voltage is √3 times of phase voltage? So we talk about the balanced three-phase connection. We talk about the balanced three-phase connection. This is the star connection. Across each winding, this is your which voltage it is? Line voltage. Suppose R, Y, P phase, IR. This is okay. This is the voltage. This is phase voltage because this voltage across each winding. Now across this this will give line voltage RY or RB. These are your line voltage between two lines, two phases. So here, if we draw this, in a balanced delta, this is balanced star connection. In balanced star connection, the phase values across each phase have a same magnitude, and they are perfectly 120-degree apart from each other. This is VR phase voltage, VR, VY, VV, RYB, this sequence. So now if we calculate a voltage between suppose R and B, VR. Okay, so we shift this transformer in opposite. So it is a vector, no? In vector, if we shift, we can. Their angle is changed. So it is a vector V negative, okay, minus V. It means now the magnitude is same. This length is equal to this. Yeah, negative. But now this angle become 60 degrees. So if we calculate their vector sum, this is your resultant of these two vectors. Okay, VRB. What is the value of BRB? How we calculate? So yesterday I told if two vectors are there, PQ, and we know the theta angle. Then this R we can calculate resultant. R square equals to P square plus Q square plus twice PQ cos theta. This this plus sign is come when this angle is acute. So why we take this side this? यहाँ पे भी हम निकाल सकते थे इसका resultant, but it is greater than 90. So we have a theta that should be less than 90. Okay. So my dear, here in delta also this individual phase for balance star na, this VR equals to Vy equals to Vv. This is denoted by V phase, and this VRB, VRY and VYB, that is represented as a line voltage. Okay, equal hai. So now if we calculate this resultant BRB, this BRB, this line, so this VRB whole square equals to VR square plus VV minus V. It is a vector, na magnitude, so it is same. Okay, V square minus VV square plus twice VR VV cos of 60 degree. My dear, they are equal na, so this we replace with the line. These are all our phase, V phase square. This is also twice of V phase square. Okay, but you know cos 60 is root 3 by 2. This 2 cancel. Sorry, 1 by 2 na cos. Okay, hello. Cos 60 is 1 by 2, like sin 30, it is equals to okay dear, cos 60 is 1 by 2. Please check. Correct na? Yes. Hello. Now this become equal now, although it becomes 3 V phase square. Then VL square equals to, then VL equals to root 3 V phase. That's why this root 3 has come here. Okay. So in oral sometime 1-2 year back, some examiner asked this question, why this root 3 has come, how it is. Okay. Correct. Now my dear, why here it is required? See, so in in delta side, suppose your transformer is 1 inch transformer. This is a primary of transformer. Okay, correct, my dear. This is your primary of transformer. Now suppose secondary side is delta connected. You know here this phase voltages, or this is VR, and then suppose this is VY, then VV. This equals to this line voltage is also like VRYB. Between RYB R and B phase. Like here, we measure this voltage between this and this wire. Then it will show you same value, or either this CR See, in between these 2 points, this voltage is same, no? The phase voltage equals to line voltage here, huh? Correct, no? So actually, now if we draw final, hello, primary side, now we compare the vector or phasor, vector diagram of primary side and secondary side, line voltage vector, line voltage phasor or vector. Line, we compare line voltage phasor. Okay. So you know your line voltage phasor here in primary side, this is your line voltage. So other will be, it is like here. Other will be, it is like here. Correct, no? So my dear, your primary side, this is your primary side, 120, 120, but these are line voltage, all three line voltages. On secondary side, that is my dear, this is all three line voltage of secondary side. Okay. So with respect to this vector, if we compare particular phase line voltage like this, so see here, there is this is 30-degree shift, 30-degree, it is leg minus. If we change the configuration, sometimes it is 30-degree lead. So there is a phase difference in primary and secondary line voltages. Okay. Correct? Generally, actually it is star delta. Your transformer is suppose star delta. Huh? So see, if suppose primary is star connected, sorry, delta, and this is your secondary. Suppose this is your primary side, is star. No, sorry, it is delta. We are talking about now delta star connection, delta star. This delta means this is the line voltage of all three line voltages. But when we initially draw, this is your this was initial diagram. Okay. This is your initial. These are star side. This is line voltage. Sorry, phase voltages. Phase voltages. Now we calculate the line voltage. So this line voltages are this. Okay. So finally we have this one. It means with respect to this phasor, it is 30° lag this voltage. Okay. Okay, my dear. Now we discuss one thing. Suppose you have a 2 3-phase transformer. Okay. Let us, they are same capacity, same turn ratio, everything, but their connection are, it is, it is suppose delta delta connected or star star. Okay. Here we take a delta star. Now tell me. Now suppose there, all three lines. Here this is the input, their input. Three-phase input. This is also three-phase input here. Either they connect with a different source or maybe same source. So this is the primary bus, no? Here, this is your primary bus bar. Maybe there they have connect from. If we talk about the like this, R, Y, B. Their phase sequence are same. We maintain the phase sequence. Okay, like here. Okay, dear. So this is the primary. Now on secondary side. Here is also R, Y, B. But my dear, what happened? They are same voltage, like this is 11 by 4, 11 kV by 415 volt. This is 11,000, you write. Okay, like 11,000 by this. This is same turn ratio. Okay. 415. Or either 6.6 kV, you write here. Means 6600. Here also 6600 means 6.6 by 0.415 or 0.33 kV voltage. Okay, but we not connect this. Why? This is wrong actually. We never operate with star with delta star. Why? Because line voltage of here and here magnitude are same. But if now you compare, like this voltage, we R phase of this transformer 1, and here is this transformer 2 R phase. If we check, see this voltage like like this line voltage phase, but the voltage it is lag with this. There is a phase difference. You know why we there is a one why we synchronize the two alternators? Hello. What is the synchronization? Means how we synchronize. Okay. We use a synchronization or either a 3-lamp method or voltmeter method. What is it is meaning? Means we connect the alternator to the bus bar when the bus bar voltage and alternator voltage are in same phase. Means there is no phase difference. If there is a phase difference, what happens? The leading, there is a circulatory current is start to flow. Suppose this voltage is lead, this is leg. Okay. So there is a internal circulatory current from this transformer to this. They supply the load. Okay, they supply the load here, 3-phase load. Okay. So there is a load current, but this transformer 1 is also feed this transformer 2. So now internal circulatory current will be flow. That is heating the transformer and losses are increased. Okay. So it is not correct. That's why we only operate same configuration. Okay, same capacity, but due to this secondary different connection, there is a phase difference in the voltages, either the lead or lag. Okay, so this is one another essential condition. Now you please write the, there is a, when we apply for a job, it is written essential qualification means condition here in transformer, and desirable. Like we have a bachelor, B.Tech. Here maybe M.Tech they can write, but it is not required. Basic qualification required, essential is only B.Tech. Same like in transformer, there is a certain or essential. Without that fulfillment, we cannot operate. But some are the another condition also that is recommended by the manufacturer to apply that condition also. Okay. What is the essential? First, this there is secondary terminal voltage. First is phase sequence. Here, phase sequence RYB, yeah, should be same. Second is please. First is phase sequence, then secondary output, terminal voltage, like magnitude, 415. Okay. Otherwise, if magnitude is different, then again the current is flow from one transformer feed other. If the higher voltage to lower voltage, therefore their no load terminal voltage should be same. Okay. Either their no load may be different because their percentage. If suppose there is a different percentage impedance, it may be okay. But after the voltage drop, we get here same voltage like V2 here, V2. Secondary, their voltage, terminal voltage should be same. In maybe there is a different, suppose their percentage impedance, if they connect to same source here, then their turn ratio should be same. This is also condition. But sometime ऐसा भी हो सकता है, this transformer 1 and 2 are coming from different source, or it may be, this may be 3.3 kV or maybe 11 kV by 4, but secondary voltage are same, 415, 415, then we can hear. This is the one way of also paralleling. In that case, their percentage impedance may be different, their turn ratio will be different. Okay, but your primary side bus bar is also common, in same source. When they connected their primary to same source. Yeah. Okay, then same turn ratio. Turn ratio. Same. Okay. Other, please. So this fourth also. They have a same vector group. This is known as a vector group. This. What is a vector? Same vector group means same configuration, same connection. Okay. These are the essential. Now desirable. Okay, maybe their percentage impedance, power factor should be same. Okay, like that. Frequency, actually generally frequency are also same, because if same source, then it is not change the frequency. Output we get also same frequency like 50 Hz. But maybe if they are connect from different source, in that case you can put the frequency of secondary is are same. Frequency you can write. Okay. Transformer is not change the frequency. That's why here in alternator the frequency terms is used. Okay. Correct, my dear. This vector group we can represent by clock phase. On nameplate of transformer, vector group is mentioned. Okay. So, on clock, suppose this is 12 o'clock, 3, 6, 9, this is 11, this is 1. Okay. So, between 2 hours of a clock, we get a 30 degree. Like 12, 11 or 12, 1. Because 12, this is 36, if you divide, comes 30 degree, 360 by 12. So this angle between 12 and suppose 11 o'clock means your hour needle is at 11, and your minute hand is, this is hour hand, this is minute hand. So there is a 30 degrees angle. Okay. It is called as 11 o'clock. Okay. So suppose at this is the minute clock, and hour we represent with either at it is 6 o'clock, then it make a 180 degree. If it is at 1 o'clock, then there is a 30 degree angle, or 11 o'clock again 30 degree. This is our needle. This is always at 12 reference pager. Okay, or it is both are overlap in 12 o'clock. So there is a 4 vector group will be possible. First is this is 0 degree, 180 degree, 30 degree minus, plus 30 degree. This configuration we can have. Okay, lagging, leading 30 degree. These are the four vector groups in transformer. Now this is called as a 12 o'clock in clock phase. This is known as a 6 o'clock. This is known as a 1 o'clock. This is called as a 11 o'clock. Okay, leading. Okay. Now, actually 0 or 180 degree, in which connection this is possible, we get when your primary, secondary are connected in either in delta delta or in star star. Same, this also. If your transformer is connected star star or either delta delta, then only we get this two. And this 30 degree, yeah, this is when your star delta or delta star. Same like this we can achieve like this. If we change na their one side connection polarity, then we get means this, if your star delta means this minus 30, we can get a plus 30 also easy way. But it is very difficult, and 0 we can get a 180 also if we change their terminal polarity. Okay, but my dear, from here to here, from this group to this group, if this change is very impossible, means it is not possible to 0 vector group to get a star delta or delta star. It is entirely you have to dismantle your transformer, then it is possible. Okay, because in star, the star point is very inside, so we cannot change the connection easily. Okay. Okay, now in your nameplate vector group it is written like, suppose your transformer is okay, the group is written like DY11 or DYN11, or sometime it is DYN1. What is it is meaning? First capital letter is show your HT side connection. It is delta connected. It is delta star, and your secondary side LV is connected in star side. Then 11 means this plus 30 degree without neutral. NH means your secondary side is a neutral, grounded is also there, neutral is there, and then 30 degree. 1 means with neutral again. Maybe we can write Y. Now Y में अभी ये नहीं हो सकते आपके 1 और 11, that is 6 or Y12 may be possible. Okay, got it? So this is written in your vector group, so means your nameplate DYN11 or DY11. Got it?
Yes, sir. This DYN1, which one? This one, do you write third one, DYN1?
One
How
minute,
we will-
minus 30 degree.
Okay, noted, sir. Noted. Thank you, sir.
Means 1 o'clock. 1 o'clock where you are now see
Okay,
here.
sir, noted. Thank you.
Yeah. your this capital letter means HT size phasor. It represents it, and your minute hand is always represent the HT side means HV line voltage. This your hour needle. This represent LV side. Like length से लिया है इसको. Length is minute hand is large, no? High voltage side. This LV line voltage it represents. So they represent the phasor. Means HV LV voltage, line voltage phasor. So there may be zero phase difference if the connection are okay. That's why now it is clear, na? We can connect the transformer with star with star only. Star with star delta also we can, because there is a same phase, na? It is possible. Okay. So this is one time this parallel condition. This vector group is also in three phase, very important. Okay. Okay, dear. So I think now one numerical we can discuss. It was asked in your exam papers in all the ETO exams. This seventh you can practice also. Huh? Okay. I already put this parallel conditions desirable and essential in group. One day. So see this sixth question. This is seventh. There is a container ship has a three-phase delta connected with 6600 by 440 volt. So let us we have a one delta connected. Here is winding up. Sorry. This is your three-phase 6600 volt. Okay, three-phase. Now secondary side. This is also delta connected. It is connected to load. Three-phase load. Here is a secondary. This is the line current. Secondary line current. Here this is the primary. One is stand for primary line current. So he said that is feeding the alternate marine power supply from source of. So here this secondary is 440 volt. This is this much voltage is given. Transformer primary take a line current. Here it is given 100 ampere, my dear. Then he asked to determine the okay, secondary load power factor is given. Here secondary cos phi 2, 0.8 lagging. Now we say determine the each coil current. Each coil current and kilowatt output of transformer. Okay, dear. So first of all, you will see primary line voltage is 6600. Then primary phase voltage equals to primary line voltage only. Why? Sorry. Because for delta connection, first we convert the line voltage we get. It is primary phase voltage. Okay. Primary phase voltage. This much volts. You can write for delta connection. For delta connection. Okay. This phase voltage equals to line voltage. Similarly, we can calculate secondary phase voltage equals to V2 phase. Also equals to secondary line voltage. It is also same. But if here is a star, then you have to divide by √3 times. Okay, please remember. First we calculate phase voltage. Now you get both phase voltages. Secondary phase voltage. You write here voltage. Primary phase voltage. This is also. Okay. Now you get both phase. Now please rewrite phase turn ratio. Phase turn ratio, or it is called as a per phase turn ratio, K. Equals to secondary
V2 upon
phase,
V1.
but phase value. But here are actually for delta, both are in delta, primary, secondary. Line voltage equals to phase voltage. That's why it is 440 by 6600 only. If it is, suppose this is star, then this will be divided by √3. Then this will give you turn ratio phase. But here it is delta also, no? Okay, then now my dear, this value give you 0.067. Now use the turn ratio. Or K equals to V2 phase by V1 phase. And then current is I1 phase by I2 phase. Okay. So here you also write primary phase current. So that is I1 phase. I1 phase. It is I line by √3, because in delta here if you calculate a current here, this is the phase current. Here also this is your this is your phase current. So actually this is called as a current in each coil, means phase current, and this is the line current. Okay, secondary, this is primary phase. So we calculate this, it becomes 100 by √3, means 57.57 735 ampere, or 74 we can write. Therefore, here we can calculate secondary phase current. My dear, please remember, when we use a phase turn ratio, then phase values, we get a phase value. Okay, so it is secondary phase current. From this equals to primary phase current divided by K, turn ratio, or it is 57.735 divided by 0.067. We get it 861.72 ampere. Okay. So this is the first part, current in each coil. Coil winding means phase current. Then second is a kilowatt output of transformer. So now here also you calculate a secondary line current or load current, secondary line. So it is I2L, na? It is √3 times of I2 phase. Please you write for star connection, for delta connection. You have to multiple with into √3. Correct, na? Because this is a phase current, this is now line current. It comes 1492.54 ampere. Now kilowatt output of transformer. √3 line current secondary voltage, secondary line voltage into secondary line current into power factor. Secondary side, okay. It is V2 I2 line. Kilowatt, for kilowatt you divide by 1000. So this √3 into V2 is 440. I2 is 1492.54 into 0.8 is the power factor, divided by 1000. Or we can say 910 kilowatt. Okay, yes. See here, this second question also, three-phase transformer has 900 turns in primary, 400 turns in secondary. Means this is per phase turn, N2 by N1. अभी थ्री फेज में लाइन टर्न्स नहीं होते हैं कोई, वो पर वाइंडिंग में बोलेगा ना, तो मिला के नहीं बात करते हैं. ओके, तो दिस इज पर फेज टर्न. मीन्स as a primary means N1, this is N2. Okay, this is per phase. So if we calculate na phase turn ratio, that is N2 by N1. It means it is 104 by 900. This give you phase turn ratio. Then is a primary is connected with a power source of 6600 from HT side, HV, high voltage side. Calculate the secondary line voltage when your transformer is star delta or delta star. Okay. If suppose primary is star, means just I will explain. You can. So suppose you first part, when in first part you make a connection, please. And secondary is delta side. So here it is given 6600 volt. This is primary line voltage. He asking the here secondary side line voltage. Okay, turn ratio, here it is N1, here it is N2. Perfect. Same, because this is a per phase turn ratio. That's why first you write primary side, primary phase voltage you write. Primary phase voltage. Because in star, this is, it become B2 phase, sorry, B1 phase, na? B1 line by root 3 means 6600 by root 3. Okay. Then we can use this formula now, N2 by N1 equals to V2 phase by B1 phase. Okay, this, if it is given 104 by 900. Now first secondary side is asked, means he is asking V2 phase. But always you answer the data given in question line values in three phase. And when you answer please write the line voltage. Now see in secondary side, if here we take this, what is the turn ratio it comes? It comes 0.55, sorry, 1155. 1155. Okay, dear. So from this V2 phase means secondary phase current, secondary phase voltage. That is 0.1155 into primary phase voltage. My dear, it comes 0.1155 into phase voltage secondary. This is the primary phase voltage 6600. Either you calculate here or you divide by this. जो ये value आएगा, this is your
Sir, primary phase voltage is equal to line voltage because it is in star connection.
yeah. But first if we calculate phase value, so this come 440 volt, 0.32 you can write or okay, like here. Now secondary is delta. Secondary is delta side. Then we can write secondary, where your answer should be in line value. Secondary line voltage equals to?
No, sir, you calculate this primary phase voltage. This should be equal because it is in star.
Star में equal नहीं होता है. Hello.
Yes. Sir, voltage. Okay, noted, sir.
Hello, audible?
Yes.
Hello. Yeah,
Yes.
can see del star side current are same. Voltage is 1 by root 3. Please.
Yes. Noted, sir.
Okay. But now delta side mein na this voltage, secondary line voltage equals to secondary phase voltage only. That is 440 only. Okay. Volts. Okay. You can write here 4 delta because it is delta connection. Okay. First part is over. Second part you make it different. Then you use the same turn ratio, but your here delta. It means this is your phase voltage equals to line voltage 6600. Then you calculate secondary side V2. That comes line voltage. Then you multiply that by root 3. Then you get a line voltage. Okay. Correct, na? Actually, when
Yes.
you
Correct.
use the when we convert from line to phase, you observe the connection. It is delta or it is star. Okay. Clearly. Okay, there. So mostly transformer we solve all the questions. All the theory part also we discuss lot of things here.
Sir, can you share your PPT of these transformers?
भी आपको संजीवनी बूटी चाहिए, हिमालय क्यों उठा रहे हैं? Okay.
Today answer question also puts at Telegram.
मैं बताइए कुछ ऐसा है चाहिए क्या है बोलिए. Okay, dear. Good evening. Yeah.
Okay. Good evening, sir.
A question answer also puts at Telegram. This today is solved.
सर नेक्स्ट कौन सा टॉपिक प्लान कर रहा है सर?
Synchronous machines.
ओके सर.
ये ऑलरेडी ये सॉल्यूशन है ग्रुप में, आप देखिए. ठीक है, दिस क्वेश्चन सॉल्यूशन.